Okay, good afternoon, everybody. I hope my audio is good. So, just some housekeeping matters first. Just a reminder, homework number one is due tomorrow at 5 p.m. So, make sure you submit your homework. Um, Also, make sure that you have downloaded the latest version of homework one. So, nagdagdag ako ng isang bonus question which is worth 1 point. Basically, that's an extra 20% kasi over 5 lang naman yung homework number one. So I'll sprinkle some of those bonus questions for some of the homework. So kindly look out for them. Wag niyo sayangin, sagutan niyo siya. And then what else? Oh, I also edited homework 2. Um, Kanina ko lang actually nabasa ng buo yung lecture note number 1 at hindi pala na-define ano yung boundary ng isang set. Tapos nagtanong ako sa homework ng something about the boundary of the set and then may typo error dun sa problem number 2 in homework number 2. So I already corrected that. So you can download it now. Make sure that what you download is entitled homework 2-2. Actually, that's the third version na ng homework 2. So kindly do that probably right now or after the class before you start attempting homework 2. The deadline for homework 2, I decided to move it to September 29th, right before midnight. So that's going to be next Wednesday or this coming Wednesday. So kesa Monday, all right? Though I hope matapos natin ngayon yung lecture notes for Unit 1. So para ready na kayo para sa homework 2. Okay? So I think that's all the updates I have for you. So may questions ba about homework 1? Though I don't want to give too much hints on homework 1 because two of your classmates already submitted their work to homework 1 and they already graded their work. So yeah. Any questions? I'll try not to spoil. So walang tanong? Okay. So if there are none, then let's proceed to our topic for the day. So, but before that, pala, let's have a recap of what we did last time. So last time we looked at the order and the completeness axioms. So we've seen that some of the fields or some of the common or the known number sets to us satisfy some sort of order, right? So sila yung mga ordered fields if they satisfy axioms 1 to 11. So they are an ordered field. Example would be, of course, the set of real numbers, then the set of rational numbers. Okay. However, what distinguishes the set of real numbers from the set of rational numbers is the completeness of R. So last time we presented two versions of a completeness axiom. The first one is sort of more abstract, which is Dedekind's completeness axiom. So probably that axiom is usually adopted for graduate courses. Now, the Dedekind's completeness axiom is equivalent to axiom A12, which is called the least upper bound completeness axiom. Or most of the times I will refer to it as the least upper bound property. So when we say equivalent, so that means we can prove Dedekind's completeness using the LUB property and vice versa. We can also prove the LUB property using Dedekind's completeness. So that means these two axioms, A12 and A12 prime, are equivalent to each other. And sabi natin, in an ideal logical discussion, dapat yung mga axioms ay independent. No axiom should be provable from another axiom. So in our development of the calculus of real numbers or real valued functions, we will just select the least upper bound property as our completeness axiom. So ito yung gagamitin nating completeness axiom. Sinasabi niya lang, walang butas yung set of complex number as set of real numbers. So between any two real numbers, there is another real number. Hindi natin kayang paghiwa-hiwalayin yung mga real numbers. That's why we're able to represent the set of real numbers using the real number line. So remember, ito yung properties ng set of ng real number line. So number one, there is an order to it because R is an ordered field. So we can arrange the real numbers in a straight line so that something to the right is greater than something to its left, right? So, ibig sabihin kung ito si A, ito si B, dahil si B ay nasa kanan ni A sa real number line, so ibig sabihin A is less than B. And that's thanks to the order axiom. And then, thanks to completeness, kahit saan ka kumuha dyan, kahit anong point ang piliin mo sa line na yan, laging there will correspond a real number to it. Kasi walang butas yung set of complex numbers. Unlike the set of rational numbers, pwede pa rin natin i-order yung rational numbers in a line. Okay? Kasi ordered field ang Q. However, may mga butas dyan kasi meron dyang mga kulang. For instance, square root of 2 is not a rational number. So that means the point corresponding here to root 2 kailangan magka-whole dyan kasi hindi siya part ni Q. So, yeah. So that's basically that's completeness in a nutshell. Okay. And then I think we also started with okay, or basically let's recall what the LUB property is. So it says that any non-empty set of real numbers which is bounded above has a least upper bound. Okay, and we call the least upper bound the supremum of that set. So any non-empty set of real numbers has a real number as its supremum. In contrast to the set of rational numbers. So dahil ang set of rationals ay hindi complete, ibig sabihin there is a non-empty set of rational numbers that is bounded above but doesn't have a supremum in Q. So for instance, kung kukunin natin yung set A of rational numbers such that x is less than root 2, wala siyang supremum sa set of rational numbers. So kasi ang possible supremum ni A ay square root of 2, but square root of 2 is not rational. Ibig sabihin, wala siyang supremum under the set of rational numbers. That means Q doesn't satisfy the completeness axiom. And that shouldn't be a shock to us because napakita natin last time that Q doesn't satisfy the Dedekind's completeness axiom. Logically equivalent naman si Dedekind's completeness at saka yung LUB property. So when a set doesn't satisfy Dedekind's, it cannot satisfy LUB and vice versa. Okay. Now, there are several statements that are equivalent to Dedekind's axiom and the LUB axiom. So nilista ko siya sa remark 1.9.2. Pero dahil ngayon inelect na natin si LUB axiom to be our completeness axiom, so all other theorems listed in remark 1.9.2 are considered to be theorems. Kasi kaya natin silang i-prove using the LUB axiom. So we don't need to assume them just to be true kasi provable naman sila gamit ang LUB property. Okay? And I guess this is where we stopped last time, corollary 1.1. So here we just proved the result or the analogous result for the infimum. So here we suppose S is a non-empty set of real numbers which is bounded below naman. Then it follows that S has the greatest lower bound in R. And again, another term for the greatest lower bound or the GLB is the infimum. So kung siya ay bounded below, lagi siyang merong real number as an infimum. Okay? And this is a corollary to the LUB property because we just used or we relied on the LUB axioms in order to prove this result. Okay? Actually, the nice result from our proof is this. The infimum of a set is the negative of the supremum of the set consisting of the negatives of the members of the set S. So infimum S is the negative of supremum of the set negative S. Okay? Now, theorem 1.7 gives us another characterization of the supremum. So kahit alam na natin na si supremum siya yung least upper bound, siya yung pinakamaliit sa lahat ng mga upper bounds, sometimes it's handy to prove that a certain number is the supremum of a set using these two conditions of theorem 1.7. So it says here that if S is a non-empty set of real numbers, then the supremum of S is equal to B if and only if the number B satisfies the following conditions. Condition 1 is that just B is an upper bound for the set S. Okay? And then second property is that for every epsilon greater than 0, there exists an element of S that is larger than B minus epsilon. So tingnan natin ano yung ibig sabihin or interpretation ni property 2. So ang ibig lang sabihin niya, remember in math, whenever we write epsilon, we usually mean something that is very small, okay? So you can imagine epsilon to be a very small number, okay? And then condition number 2 says na kapag ka daw si B, which is an upper bound by virtue of condition 1, binawasan mo ng kahit katiting, binawasan mo kahit epsilon by some number epsilon greater than 0, however small it is, hindi na siya nagiging upper bound because there will be an element of S that is larger than B minus epsilon. So ibig sabihin si B, kung siya nga yung supremum, ibig sabihin sagad na siya. Hindi mo siya pwedeng bawasan ng kahit na maliit na value kasi pag binawasan mo siya ng kahit napakaliit na number, hindi na siya magiging upper bound. Okay? So yun yung idea ng supremum, sagad na siya. Okay? So you have the proof there at the bottom of page number 9. So you can read it on your own probably. The thing here is that this is an if and only if statement. And remember that an if and only if statement can work as an alternative definition. Kasi twofold yung proof niya. So here you are actually claiming two things. Number one, if it is the supremum, then the two conditions automatically follow. Right? And the converse is also true. If these two conditions are satisfied, then you can conclude that B is the supremum of S. So basically, at the back of your minds, you can treat this theorem as an alternative definition or a characterization of being a supremum. Okay? So posibleng hindi mo na, kasi minsan, lalo na kung computational yung proof, mahirap ipakita na wala nang mas maliit na upper bound kaysa kay B. Pero one way to do that, at least analytically, is to show that when you take away epsilon, however small that epsilon is from B, the difference, B minus epsilon, cannot be an upper bound for the set S. Okay? Kasi nga, sagad na yung supremum. Alright? So this might be helpful in future proofs, so kindly take note of that. And of course, if you have a result for the infimum, for the supremum, there might be an analogous result for the infimum. So in theorem 1.8, we suppose that S is a non-empty set of real numbers, and we let L to be then L will be the infimum of S if and only if these two conditions are satisfied. Again, it's an if and only if statement, so it's an alternative definition. Condition number 1. X is larger than or equal to L for all x's in S, meaning L on itself is a lower bound. And then second, for any epsilon greater than 0, however small it is, there will always exist an x in S such that x is smaller than L plus epsilon. So, ganun din, ang infimum daw ay sagad na rin. Kasi kung dadagdagan mo yung infimum, even by a very tiny amount, hindi na siya magiging lower bound because you will be able to find an x in the set S that will be lower than L plus epsilon. So, pag dinagdagan mo siya ng kahit katiting, nalulose na yung property ni L plus epsilon as a lower bound. Okay? Kasi meron ng isang element ni X na magiging mas maliit kaysa kay L plus epsilon. Right? Okay, I hope these two theorems make sense, at least from an intuitive point of view. Hopefully, we will encounter later some results wherein 1.7 and 1.8 will be useful. Actually, I think you can use these two results in doing or improving exercises 1, 2, 3. This should be 4. And then this should be 5. Medyo mahirap lang yata yung exercise 5. Isip ko kanina kung ano nga ba yung proof ng equivalence ng dalawa. And I'm not sure if that is easy. Medyo technical din yata yung argument. There might be an easier proof, but I cannot think of it right now. So, pwede nyo yung i-Google. But again, if you are Googling a proof, make sure that you can paraphrase it or rewrite it into something that you understand. Okay? Now, the main course for today would be the consequences. Consequences. Mali yata yung spell ng consequences. So, okay. So probably later today or early tomorrow, I will upload a revision of the lecture notes. So kindly watch out for that. Iko-correct ko yung mga tiny typos here. So here are some consequences of the completeness axiom. The first one is theorem 1.9. The set of natural numbers is not bounded above. Okay, so this is something that we already know from elementary days na hindi ka matatapos mag-count if you are to enumerate the natural numbers because the set of natural numbers is not bounded above. And the proof is actually quite simple because again, we know the set of natural numbers to be the set 1, 2, 3, 4, 5, and so on. And we will take advantage of a proof by contradiction. And again, in a proof by contradiction, we assume the negation of the conclusion. Okay, so the conclusion here, or the thing that we want to prove, is that n is not bounded above. So let's suppose otherwise. So for the sake of contradiction, let's assume that n is bounded above. And since n is assumed to be bounded above by the LUB property, because n is a non-empty subset of R, tama? So by the LUB axiom, there is a least upper bound for n. Tapos dun sa proof tinawag siyang B. Okay? So dahil meron siyang least upper bound, that means for any little n that is a natural number, then n is less than or equal to B by virtue of B being a supremum and hence an upper bound in the first place. Okay? But remember a property of natural numbers? Kung si m ay natural number, ibig sabihin si m plus 1 ay natural number din by rule of succession. Alright? So m is a natural number, m plus 1 then will be a natural number. Pero ang usapan, remember from our previous statement here, kapag kasi n ay natural number, ibig sabihin dapat mas maliit siya or equal kay b. But here we know that m plus 1 is another natural number. So it follows that m plus 1 must also be less than or equal to b. Okay. But that statement will mean m is less than or equal to b minus 1 for all natural number n. Kasi yung antecedent dito ay nag-work sa kahit anong arbitrary m that is a natural number. Ibig sabihin, pagka nag-subtract lang ako ng 1 to both sides, or if you want to be technical about it, when I add the inverse of 1 to both sides of the inequality, I'm going to get m less than or equal to b minus 1, and that will be true for any arbitrary m in n. Okay? But there, we notice a contradiction. Bakit kaya may contradiction? Anybody who wants to try? Bakit may contradiction dun sa m being less than or equal to b minus 1? Walang gusto mag-try? Okay. So I say there is a contradiction because ang lumalabas dito, si b minus 1 pala ay upper bound para kay n din. Kasi si b minus 1, sabi natin ay mas malaki sa lahat ng natural number n. So b minus 1 then is an upper bound. But we said that b is the least upper bound. And yet we have found another upper bound, namely b minus 1, which is smaller than the supposed least upper bound b. And hence that cannot happen. So therefore, we must accept the negation of our supposition and cannot be bounded above. And that completes the proof of theorem 1.9. And you see the power of the proof of contradiction. Principio de reductio ad absurdum. Okay, so we are reducing this argument into a contradiction. We have shown that the negation of the theorem that we want to prove cannot be accepted to be true kasi may mababiolate tayong previously assumed or previously proven fact. Okay? So from now on, we can sleep at night soundly kasi na-prove na natin ang set of natural numbers ay hindi bounded above. Okay. Oh, I think this is our proof of corollary 1.1 from last time. Okay. Okay, any question before we move on to the next result? Mag-react naman kayo, guys. Okay, so if no reactions, then I'll go on to the Archimedean property. And I guess the Archimedean property is one of those results that I said is equivalent to the LUB property. So that's a clue that here, probably in the proof, I will use the LUB property. Okay? So the Archimedean property says that if epsilon is a number greater than 0, then there is a natural number n such that this inequality is true. Remember, epsilon always stands for, almost always stands for a very small number. So sabi ng Archimedean property, kahit pa gaano kaliit yung epsilon, okay, meron kang mahanap na natural number such that 1 over n will be smaller than epsilon. Okay? Which basically makes sense kasi parang ang nangyayari lang ay kung maliit yung epsilon, eh dilakihan mo yung n. Tapos hindi naman tayo mauubusan ng natural number n kasi nga unbounded above yung set of natural numbers. And the bigger the natural number is, the smaller 1 over n is. Okay? Tapos sabi ng theorem na to ng Archimedean principle, laging kayang-kaya nating palitin yung 1 over epsilon or 1 over n compared to a very small number epsilon. Okay? So let's read the proof. I hope okay lang na kapag yung proof naman ay feeling ko ay madali, ang gagawin ko lang ay babasahin ko na lang or babasahin na lang natin yung proof on the lecture notes para rin masanay kayo kung paano magbasa ng isang proof. Okay? So, pero hihimayin natin or lalagyan natin ng mga detalye whenever there are some missing details in the proof. Okay. All right, so let's see how it is done. And I guess it is again done by contradiction. So, kasi kung gusto mo ng direct proof, the only proof is to construct such, to find such an n. Kasi this principle claims na kahit ano pa yung epsilon na ibato ko sa inyo, lagi kayong may mahanap na n such that 1 over n is smaller than epsilon. Okay? So, medyo mahirap yung direct proof kasi kailangan kong i-construct yung 1 over epsilon, yung 1 over n. So, let's try proof by contradiction, and I guess that is what is done here. So again, let's negate the conclusion. Sabi ng theorem, kahit anong epsilon, may mahanap akong natural number such that inequality holds. Okay? So, the negation would be, kunwari, walang natural number such that this is true. Okay? So, pag binigyan ko kayo ng isang epsilon, so probably kulang to assume that for some epsilon greater than 0, there is no natural number n such that 1 over n is less than epsilon. Sabi kasi sa corollary sa Archimedean property, kahit anong epsilon, may mahanap kang n. So ang negation niya, merong isang epsilon na wala kang mahanap na natural number n such that the inequality is true. Okay? And if that is our assumption, then for this specific epsilon, sa lahat ng n, laging mas malaki or equal to epsilon yung 1 over n. Again, this is what is meant by our supposition kanina. So dun sa specific epsilon na napili ko dito sa assumption na to, kahit anong n pa yung piliin ko, laging mas malaki yung 1 over n kaysa kay epsilon. Okay? And then I can multiply both sides by n and divide both sides by epsilon. Anyway, n and epsilon are both positive real numbers. I will get this inequality in return, that n is less than or equal to 1 over epsilon. Okay? And I guess here, there's already a contradiction. Anyone who can tell me what the specific contradiction is? Kunwari, hindi nyo nababasa yung susunod na sentence. Ano yung contradiction dito or bakit may contradiction dito sa highlighted portion? Anyone? Wala talaga? Tahimik nyo ngayon, ha?
Hello po.
Okay, go ahead.
Ito po ay kasi dahil the natural numbers are not bounded above.
Exactly. Thank you, Joshua. So prove lang natin kanina na set of natural numbers ay hindi bounded above. But here, look at what we said. For every natural number n, si n ay laging mas maliit or equal to 1 over epsilon. So that means the set of natural numbers is bounded above by 1 over epsilon, which is absurd. Kasi nga, kakaprove lang natin na hindi pwedeng mabound, hindi bounded above ang set of natural numbers. Okay? So since there would be something very wrong if we will accept the negation of the Archimedean property, therefore we must accept the Archimedean property to be true. And so we say na kahit gaano kaliit yung epsilon, laging may natural number tayong mahanap such that 1 over n is less than epsilon. Okay? And that ends the proof. Parang ang simple lang ng mga statements, no? Pero pag tayo na yung gagawa, medyo abutin tayo ng matagal bago maisip yung mga arguments. Okay? So that's why you need to practice and practice whenever you find the time. Kasi proving, I don't think there's an easy way how to teach proving. Parang instinct lang yan. Nade-develop niyo yan habang you answer problems more often. Okay? Now, remark 1.11 presents an alternative version of the Archimedean property. Usually, ito yung ginagamit kong version ni Archimedean property kasi madali siyang tandaan. Kasi ang sabi niya lang ng alternative version, pag meron kang kahit anong dalawang real numbers, A and B, laging kaya mong i-multiply si A ng isang natural number, okay, such that the product NA is always greater than B. So kaya kong mapalaki yung isang multiple ni A kaysa kay B. So, yeah. Pero I think for limits, mas useful yung corollary 1.2 kaysa dun sa remark 1.11. But again, these two results are equivalent to each other. Actually, sometimes some texts use this as their Archimedean property. Tapos ito ay posibleng corollary or remark lamang. But for us, let's call this the Archimedean property and refer to this as the alternative Archimedean property. Okay? Di kasi ako fan nung nagko-quote ng result number. Ayoko nagsasaulo ng mga number ng mga corollaries. Mas okay tandaan yung mga pangalan. Okay? Now, right? Okay. The next is another very important result. Oh, yes. Carlo, you have a question?
Sir, I just have a question on that last one. So for that alternative Archimedean property, if A equals 0, 0, real number A, right? So if A equals 0, does that still hold?
Okay, thank you. Nice catch, Carlo. So, kapag ka nga naman si A ay 0, kahit anong i-multiply mo kay 0, 0 pa rin yung makukuha natin. So, it cannot be greater than B. So, yeah, there is something wrong with this. Anong kulang? Paano natin ito re-remedyan? Maybe we can say positive. Yeah, I think this should be for each pair of positive real numbers. There is a natural number n for which na is greater than b. Kasi magkakaproblema rin ako kung negative, no? Kung si a ay negative, tapos si n ay natural number, the product will be negative and that will not be greater than any positive number b. So thank you, Carlo, for bringing that up. So kindly edit remark 1.11. It should read for each pair of positive real numbers. And I guess that is sufficient already. Tama nga ba?
Mukhang tama.
Okay na siya, no? But I'll double check and I'll put it in the revised version of the lecture notes. Okay. All right. So let's see. Okay. Now moving on. This is a very nice result, and this is the density property of Q and R. So it says here that this is theorem 1.10. For any two real numbers x and y, if x is less than y, then there exists a rational number r such that r is between x and y. So in a nutshell, the density property says sa pagitan ng dalawang real number, laging may rational number. Okay? So ibig sabihin ay siksikan yung mga rational numbers sa set of real numbers. Kasi sa pagitan ng kahit anong dalawang real number, may makikita kang isang rational number. Okay? And let's try to prove it from scratch. Hopefully matandaan ko siya. Though I found some typo errors in the proof. Pero mas gusto ko siyang i-discuss ng hiwalay. Kasi medyo maraming pasikot-sikot yung proof. So let's try this. Okay. So proof. So here, okay, so sabi dito, ang ating assumption lang ay x and y are real numbers with x being less than y. And we only assume x to be less than y so that we have the inequality in the conclusion. It doesn't matter, you just relabel x and y if y happens to be less than x, okay? Now, and then we want to show that there exists a rational number r such that the following inequality holds. So r is strictly between x and y, okay? Now, I will split my argument into two cases, okay? Case one is when the difference between y and x is greater than 1, okay? Kunwari, yung distance between y and x ay mas malaki sa 1. Okay? And then this is a clever trick. I will define a set S. So let S to be this set of all integers z such that x is greater than z. Okay? So essentially, kinolek ko lang into set S lahat ng integers na mas maliit kaysa kay x. Okay? And then what do you think would be, okay, so if I have this set and the very way S was defined, we see that x is an upper bound for S. Tama? Kasi lahat ng elements ni S, mga integers nga sila, pero lahat sila mas maliit kaysa kay x. So by definition, or I can say clearly, x is an upper bound for S. Then by the LUB property or by the completeness axiom, remember from now on when I refer to the completeness axiom, I mean the LUB property. Okay? Or minsan pagbabaliktarin ko yung terms, pero pag completeness, laging LUB property dapat. Okay? Yun yung dapat nasa isip nyo. So by the completeness axiom, there exists an L in R such that L is the supremum of S. Okay. So laging meron, dahil bounded above si S, non-empty siya, so ibig sabihin, LUB property will kick in, laging may real number na supremum si S. Okay. Good so far? And then would you agree that L must be a member of capital S? Okay? So agree ba kayo na si L dapat ay naka capital S? Kasi ano ba yung laman ni capital S? Ang laman ni capital S ay mga integers. Tapos yung mga integers na yon ay hindi lalampas kay X. So ibig sabihin may maximum element si S. Kasi titigil siya bago ka umabot kay X. Therefore, merong integer right before the value, the real number X. And that integer right before X actually will be our supremum. So maybe another way of writing this is that L is not only the supremum of S, but is also the maximum of S, which belongs to S. Okay? May objections ba doon? I hope it's clear bakit naki-capital S yung supremum. Because it doesn't necessarily follow that the supremum belongs to the set. Pero in this case, it is. Kasi merong maximum member yung set S. Kasi mga integers lang sila up to some point. So ibig sabihin, that turning point right before, or the integer right before X is the maximum of S. And if there is a maximum in the set, it follows that that maximum value is also the supremum. Okay? Bakit gusto kong i-insist na si L ay naka-capital S? So, this means that L plus 1 must be less than, must be greater than X. Agree? So yung supremum ng set ay nakay set S, right? Siya yung maximum integer in the set. Then I said here that it follows that L plus 1 is greater than X. Bakit? Can you justify that line or that sentence? Why does it follow that L plus 1 must be greater than X? Anyone? Or pagod na kayo? Hindi na kayang mag-isip. Hindi na gumagana yung mga brain cells. Okay. Si L plus 1, hindi pwedeng maging mas malaki kay X. Kasi ibig sabihin, kung si L plus 1 ay mas malaki kay X, ibig sabihin ay what? Mali pala yung iniisip ko. Wait. Bakit si L plus 1 dapat mas malaki kay X? Ano yung mababiolate ko kapag si L plus 1 ay mas maliit kay X? Nawala rin ako. Bakit? Bakit yung L plus 1 ay greater dapat kay X? Ano yung alam natin about L? So, alam natin si L ay yung maximum. Pag nagdagdag ako ng isa sa kanya, dapat mas malaki siya kay X. Because otherwise, anong mangyayari? Kung si L plus 1 ay mas maliit kay X, anong mangyayari? Anong consequence nun? So maybe I should put that here because otherwise, okay, meron ba nang nag-attempt? Christine, yeah, I think I saw you unmute yourself.
Ano po, sir? Kasi po kapag yung L plus 1 is less than or equal to X, edi ibig sabihin po yung L plus 1 po is also element ng set S. Eh di ba po nagsabi po tayo na si L ay ang maximum or yung least upper bound ni S. So therefore, contradicting po siya kasi po may L plus 1 po pala na nag-exist sa set S. Ayun po.
Hey, yep, great. Thank you, Christine. That's exactly correct. So here, because otherwise, L plus 1 will be a member of S, violating the fact L being the supremum of S. All right? So, okay, meron na akong L plus 1. So actually, ang niluluto kong argument dito, si L plus 1 yung maging rational number sa pagitan ni X and Y. So ano na lang yung kulang? So now, I'll use a different color here. We want to show that L plus 1 is actually less than Y naman. Kasi pag napakita natin na yung L plus 1 ay mas maliit sa Y, ibig sabihin si L plus 1 ay nasa pagitan ni X and Y. And what is L? L is an integer. Integer plus 1 is another integer. And if it's an integer, it is a rational number. Tama? So, paano ko mapapakita na si L plus 1 ay mas maliit kay Y? Okay, remember, ano yung alam natin relation between X and Y? We assumed for case number 1 that the difference between Y and X is greater than 1. So, ibig sabihin, from our assumption, from case 1's assumption, okay, we have Y minus X is less than 1, or this is equivalent to saying that Y is greater than X plus 1. But we knew that X is larger than S, right? X is larger than L. Mas malaki si X kesa kay L. So pagka si X pinaltan ko ng something na mas maliit, in particular, if I replaced X by L, I'll get a smaller number, right? Kasi si L mas maliit kay X, so therefore yung L plus 1 mas maliit kesa kay X plus 1. And this shows that Y is greater than L plus 1. So therefore, L plus 1 is strictly between X and Y. And we have proven the density property at least whenever the difference between Y and X is greater than 1. But there is a missing case. Meron pa tayong mga hindi na cover sa case 1, which is basically the case when Y minus X is less than or equal to 1. Okay. So, ito yung gagawin kong assumption dito. So, for case 2. And if we will be able to prove this, then we are done. Because we have already proven the case kapag yung difference ay mas malaki kay 1. Tapos pag na-prove natin na totoo rin siya kapag yung difference ay less than or equal to 1. So by the trichotomy axiom or the trichotomy property, ibig sabihin na-prove na natin siya sa kahit anong pair ng real numbers X and Y. Okay? Pero what could be said when Y minus X is less than or equal to 1? So this case actually covers whenever X is very, very close to Y, right? Kasi yung distance nila ay mas maliit kay 1. So, and then, I'm dealing here with something na napakaliit. So perhaps I can involve epsilon here. So, and what result do we have with epsilon? We just recently proven the Archimedean principle. All right. So that means here I can say that what? Okay. So we can apply the Archimedean principle. I'll just write AP for the Archimedean principle with epsilon equal to y minus x. Because again, the Archimedean principle applies for any epsilon greater than 0. So we know that y is greater than x, and it's just that y minus x is less than or equal to 1. It's a perfect ingredient for the Archimedean principle. Kasi nag-work siya sa kahit gaano kaliit na epsilon. Okay? So kung ito yung epsilon, so therefore, it is, we know that there exists a natural number n such that 1 over n would be less than epsilon. Yan yung sabi ni Archimedean principle. Okay? Pero yung epsilon, gamitin natin epsilon ay si y minus x. Actually, that's what I wrote in here. I'm using AP with epsilon equal to y minus x. But since n is a natural number, it's positive. I can multiply both sides by n, and I'll get 1 less than ny minus nx. Or I can just, okay, what do we have here? Yung distance between ny and nx ay mas malaki kesa kay 1. And isn't that familiar? Hindi ba ito rin yung eksaktong case number 1? So, yung y nga lang napalitan ng ny, yung x napalitan lang ng nx. Pero na-prove na natin sa case 1, kahit anong real numbers na ang pagitan nila ay ang distance between them ay mas malaki kay 1, it will automatically follow na merong real numbers, merong rational numbers sa pagitan nila. And here we are in case 2, we have transformed the case 2 assumption into something involving two real numbers, namely ny and nx, na ang distance between them ay mas malaki kesa kay 1. So pwede ako mag-appeal sa case number 1. So by case 1, there will exist a rational number, let's call it r, such that nx is less than r, less than ny. This is a strict inequality. Tama? Ginamit ko lang yung result sa case 1 kasi nasatisfy ko yung assumption ng case 1. Okay. And then, since here I want to show that there exists a real number between x and y, but the inequality I have here involves nx and ny. But that's not hard to get because I just need to simply divide all sides of this inequality by n. And that's fine because n is a natural number. Hindi nababago yung inequality pag nag-divide ng positive number, right? So that means this implies x is less than r over n less than y. And since r is in Q, then r over n is also a real number. A rational number. And so it doesn't matter whether the distance between y and x is larger than 1, or if it's infinitesimal or very small, there will always exist a rational number na nakasingit dun sa pagitan ng dalawang real number na yun. And that's essentially what the density property means. Okay? Questions? Clarifications? Does the proof make sense? Or may malabo bang part? Huwag mahiyang magtanong kung may tanong. Wala talaga, ayun yung mag-react. Any questions? I hope the proof makes sense. Thumbs up naman dyan kung naintindihan yung proof. Okay, thank you, John Edmar. Okay, now I see reactions. That's better. Libre naman yung reaction button, so pwede nyo yung gamitin. Okay, let's see. Okay, let's see some other consequences. Okay. And I think this proof also used that same argument I used. Medyo gusto ko lang siyang i-present ng step by step at hindi crowded na paragraph. And I have a couple of corrections here, so either take note of these or just wait for the edited lecture notes that I will upload. Somebody trying to speak? Go ahead. Sorry, may nagtatanong ba? Hindi ko marinig yung audio. Probably because of my connection. So if you are trying to speak and I cannot, I do not recognize you, please put it in the chat instead. Kasi nung pinanood ko yung recordings natin nung first meeting or recording nung other class ko, may nagsasalita pala pero puro static lang yung naririnig ko from my end. And it's not, it's just until when I watched the video ko nakita or na-recognize so may nagtatanong pala. Okay? So just call my attention if you are trying to speak and I am not recognizing you. Okay? Okay. Let's look at part 1.1. Oh, CK, are you trying to say something?
Ay, sorry, wala po, sir. Sorry.
Okay, no problem. Okay. All right, so there is a similar result for irrational numbers, and that is theorem 1.11. So sinasabi niya lang sa pagitan ng dalawang real numbers, laging may nakasingit na irrational number. Okay. And the proof is left as one of the exercises. I imagine it will involve a similar argument as what we used here. Kaya lang yung hindi pwedeng n plus 1 yung gamitin kasi ang L plus 1, kung si L ay integer, yung L plus 1 ay rational. So you need to think of a rational number to begin your argument with. Okay? Then you can try some of the exercises here. Probably sa problem set, I'll pick a couple of problems from the exercises set. So if you have still some time before the problem set, before I release the problem set, you can try the exercises. And I promise you I'll pick 1 or 2 problem set problems from the exercises. Okay? Para hindi masayang yung effort ng pagsasagot ng exercises. Okay. Let me see what's next. Okay. Now, we'll talk about some topology in the set of real numbers. Pero tama nga ba? Nakapag-take na ba kayo ng math 138 nga ba yun? Topology? Do you have a prior topology course? Parang narinig ko sa bagong curriculum ay meron yatang topology before mag 155. Tama ba yun? Okay. So probably these are not new to you. So when we talk about open and closed sets, epsilon neighborhoods, boundary, closed sets, open sets, and so on. But of course, I invoke the meta-axiom of ignorance. So pag hindi ko siya dinefine sa klase, ibig sabihin, hindi natin siya pwedeng pag-usapan or hindi natin siya pwedeng gamitin. So this section is devoted on defining what open and closed sets in the set of real numbers are. Sa topology yata mas generic yung kinonsider yung open and closed sets. Pero luckily for us, we are only interested with closed and open and closed subsets of R. Okay. So we have definition 1.7. So here we define what an epsilon neighborhood of a real number A is. So an epsilon neighborhood where epsilon is a positive number, usually in analysis again, the interesting values of epsilon are the small ones. Pag gumamit ka ng variable na epsilon, laging gusto mong gamitan siya para sa maliliit na numbers. Though mag-work din naman siya para sa malalaking numbers kasi ang condition lang naman ng epsilon ay greater than 0. But it is an unwritten rule in math that the significance of the use of the variable epsilon lies on epsilon being very, very small. Kaya dati may meme na, how do you offend a mathematician? You either let epsilon be less than 0 or epsilon be a large number, which is kind of uncomfortable or cringy for mathematicians, okay? But let's see. So what is an epsilon neighborhood? So an epsilon neighborhood of a number A is the set of all real numbers whose distance from A is less than epsilon. So, and we denote this neighborhood by B sub epsilon of A. So, kaya B kasi open ball sa topology yung tawag sa kanya. So, kung ito yung real number line, hanapin mo lang si A. Ang epsilon neighborhood niya ay lahat ng x's that is within epsilon distance from it. So, parang isa siyang open ball o isa lang siyang interval centered at A with radius epsilon. So, epsilon units sa kaliwa, epsilon units sa kanan. Okay? So, essentially, what you'll get is the open interval A minus epsilon until A plus epsilon. I guess it is remarked here. Siya lamang ay open interval centered at A with radius epsilon. Okay. Now, that's pretty straightforward, but I need the concept of epsilon neighborhoods in order to define what an open set is. Okay. In definition 8, we see here that a set O, which is a subset of R, is open if and only if for all points in the set, there will always exist an epsilon neighborhood that is properly contained in the set O. So, ibig sabihin lang, kung open daw yung set mo, kung meron kang open set, ibig sabihin, kahit kumuha ka ng kahit anong element ng set na yon, tapos bumuo ka ng epsilon neighborhood, kahit anong epsilon neighborhood nung set na yon, however small or big that that epsilon is, existence lang pala to, no? Lagi kang may mahanap na epsilon neighborhood na nasa loob ni O. So let me repeat that. Open yung set kapag kumuha ka ng kahit anong member ng set, lagi kang may mahanap na epsilon neighborhood niya that is properly contained in the set. So graphically, sa set of real numbers, mas madali lang siya. Okay. Kung ito yung set O, gawa mula dito hanggang dito, ito yung set O. Matetest mo kung siya ay open kapag kumuha ka ng kahit anong element niya. Okay? Bawa, kunin ko to. Meron ba akong epsilon neighborhood na makukuha around A that is properly contained in O? Actually, yes, I can pick this epsilon neighborhood. And I don't need to have a big neighborhood kasi existence lang naman. Existence ng isang epsilon neighborhood that is properly contained in O. Of course, pag nilakihan niyo yung epsilon, posibleng mas malaki yung epsilon neighborhood kaysa kay O. Pero existence lang naman yung kailangan. Okay. Now, kung nandito yung A, or let me call it A prime, may makukuha pa ba akong epsilon neighborhood niya? Well, actually, yes. I can choose epsilon to be that small. Okay. And actually, I can do this based on this illustration. I can do this for any member of the set O. And that says that the set O, which per my illustration is an open interval. So open siya. And that is actually true. You see in example 1.3, example 3, that any open interval is an open set. Okay. Kung pupunta ka sa R squared, or larger dimension, open set siya kapag laging merong epsilon neighborhood. So kung pumili ka dito ng element na to, meron ka lang open ball, properly contained pa rin siya dun sa set big O. Kaya ibig sabihin, open pa rin itong set na to. Kasi kahit anong element ng set, lagi akong may mahanap ng mga epsilon neighborhood na nasa loob ng set. This is in contrast when I have a closed interval. Meron akong closed interval AB, and I say my set O is the closed interval AB. Siguro alam niyo na kung bakit closed interval kasi nga hindi siya open, though hindi rin nagpa-follow na ganon. Pero I mean, if I take this as my test point, okay, meron akong makukuha ang epsilon neighborhood. Kung ito yung pipiliin ko, meron akong epsilon neighborhood. Pero ang usapan, I should be able to do this for all members of the set O. Pero yung set O ko dito ay closed interval AB. Ibig sabihin, kasama si A at kasama si B. Pag pumunta ako kay A, dahil member siya ni O, kailangan ko siyang hanapan ng neighborhood, ng epsilon neighborhood. But if you look at this, no matter how small I choose epsilon to be, kahit gaano pa kaliit yung epsilon, kahit ito lang yung epsilon ko, lagi siyang merong element na nasa labas ng set O. Alright? So that means any epsilon neighborhood centered at the boundary A is not properly contained in the set O. Kahit gaano pa kaliit yung epsilon na piliin nyo, laging merong element sa labas ni big O. So that means this is not an open set. Okay? Now, example 1.3.3 gives us the usual examples of open sets. Number one is the set of all real numbers. Lagi siyang open kasi ito naman yung set R. Obviously, kumuha ka ng kahit anong real number, kahit anong epsilon neighborhood, kahit papalakihin mo si epsilon, lagi siyang subset ni R. So, ibig sabihin, si R on itself is an open set. Okay? Now, another example is the empty set. Yung empty set ay open din kasi wala siyang laman. So, edi wala akong matetest na element. So, vacuously, the empty set is an open set. And then, as we have mentioned, an open interval is also an open set. Okay, so I hope you can visualize open sets. Laging mas madali sa analysis kung ida-drawing nyo. May mga reason kung bakit yan yung pangalan ng mga terms dito. Kasi they will make some intuitive sense if you try to draw them up. Okay? So let's try proving theorem 1.12. Okay, I wrote it here. The union of an arbitrary collection of open sets is open. And number two, there's a second part. The intersection of a finite collection of open sets is open. Okay. Let's prove them one after the other. Let's try the first one. Okay. So, union ng kahit anong collection ng open sets is open. Probably here, I will let maybe I can let O sub lambda, gayahin ko yung notation sa notes, such that lambda comes from an indexing set. Okay. Ang indexing set ko ay lambda. So kasi hindi sinabi na finite, wala siyang restriction kung gaano karami yung laman ng collection. Kasi sabi dito, arbitrary collection. So kahit kumuha ko ng infinitely many open sets, then that's fine. According to theorem 1.12, when I take their union, ang union pa rin daw nila ay open pa rin. Okay? Let's see why. So here, and gamitin ko yung big O to denote the union ng lahat ng members ng family. So kunin ko yung union ng lahat ng O sub alpha, O sub lambda, where little lambda is an element of capital lambda. Okay? Tapos gusto kong ipakita that this is open. So we want to show that O is open. Okay. Maybe we can use this notation para sa pagiging open. O tapos subset pero may gantong bilog. Hindi ko alam po anong tawag. So when we say O, this is read as O is an open subset of R. So dagdag notation natin para hindi na natin isusulat ng madalas yung phrase na is open. Okay? Now, in order to show that O is open, we need to show that for every element of O, there is always an epsilon neighborhood that is a proper subset of O. So kailangan kong pumili ng isang random na element ni O, tapos ipakita na laging merong epsilon neighborhood that is properly contained in the set O. Okay? So for that, I will let X be a random member or an arbitrary member of the set O. Okay. Anong alam ko ba sa set O? Ang alam ko, yung set O ay union ng mga O sub lambda. Dahil si X ay member ng union, ibig sabihin member siya ng at least isang big O of lambda or big O sub lambda. So kasi nasa union siya. So ibig sabihin nasa isa siya, at least isa dun sa mga nasa loob ng union. Okay? So that means there exists a lambda in capital lambda such that X is in big O of lambda. Okay? But what do we know about the lambdas or the O sub lambdas? The O sub lambdas are open sets. Probably nakalimutan ko pala siyang sabihin. With big O sub lambda is an open subset of R. Okay? Kasi yun yung assumption. Ang i-union ko ay mga open sets. So dapat yung mga O sub lambda ay mga open sets. Okay? So going back, alam ko na ngayon na si X ay nagbe-belong sa at least isang O sub lambda. Okay? Pero ano si O sub lambda? O sub lambda is open. So therefore, this means there exists an epsilon greater than 0 such that the open ball or the open set centered at X with radius epsilon is properly contained in big O sub lambda. Tama? Since big O sub lambda is open. Okay, is that fine? Pero ano nga yung goal natin? Ang goal natin mapakita na yung meron kang meron kang epsilon neighborhood around X that is properly contained in big O. How can I get to that? Ang alam ko pa lang, meron akong epsilon neighborhood na subset ng big O lambda. Ano ako makaka-jump ngayon dun sa pagiging subset ng set capital O? Remember set theory? Okay. So note that yung set O sub lambda is a subset of the union. Tama? Kasi yung union, pinagsasama-sama lang natin lahat ng mga elements ng big O sub lambda. Okay? Mukhang dapat pala lambda prime yung ginamit ko dito. Just to be consistent with notations. Okay? So dahil si O sub lambda prime ay subset ni O, tapos yung epsilon neighborhood ay subset ng O sub lambda prime. So therefore, the epsilon neighborhood centered at X with radius epsilon is also a subset of O. So that is O is open. Okay? Kasi napakita na natin na pag kumuha ako ng kahit anong arbitrary element ni O, lagi ako may mahanap na epsilon neighborhood centered at X, radius epsilon, such that it is properly contained in the set O. Okay? So the gist of the argument is using the fact that that a set is a subset of a union that includes itself. Okay? Now, the second part of the proof is a little bit more specific, because if you remember here, may condition, intersection ng finite collection ng open sets. So here probably I can say let O sub 1, O sub 2, until O sub n be open sets. Okay? Wala akong condition sa kanila, kundi sila ay finite listing lamang ng mga open sets kay R. Okay? and I will denote by O their intersection. Okay? Now we want to show that O is open in R. So ibig sabihin lang, kailangan ko na naman kumuha ng isang test element, arbitrary element of O, and I want to find an epsilon neighborhood that belongs to O, or that is properly contained in O. So let's do that. Random element. So I'll choose X, be an element of O. Pero dahil si X ay element ni O, at si O ay intersection ng mga O sub I, so ibig sabihin, si X ay element ng O sub I for all I starting from 1 until big N. Kasi nasa intersection siya ng mga O sub I. To be in the intersection, you should belong to all of the sets inside the intersection. So that means X must be in every one of the O sub I's. Okay? Pero anong alam natin? Yung mga X sub I's ay mga open sets in R. So that means there exists an epsilon sub I greater than 0 such that the open ball centered at X radius epsilon sub I is a proper subset of big O sub I, and this is true for all I from 1 to N. Ang medyo technical detail lang dito, alam ko na meron laging open ball centered at X na nasa loob ng mga big O sub I. Pero yung epsilon o yung radius ng mga neighborhoods na yon, posibleng mag-vary sa bawat isang set O sub I. Pwedeng sa O sub 1, ang epsilon ko ay 1/2, sa O sub 2, ang epsilon ko ay 1/3, and so on. That's why I need to be extra careful with that. And I will put a subscript to denote na posibleng iba-iba yung epsilon sa bawat isang big O sub I. Okay, so remember our goal, makahanap ng epsilon neighborhood ni big O sub I. Makahanap ng epsilon neighborhood centered at X with radius epsilon. Kaya lang, we have a bunch of epsilons here at alam ko sila ay subset lang ng big O sub I. Okay? Now, what could be the proper choice for epsilon now? Para yung yung epsilon neighborhood centered at X with radius epsilon ay mag-belong dun sa intersection. Ano kaya yun dapat kong pilian to be my epsilon? Anyone? Kasi ngayon may mga candidates na ako. Epsilon 1 hanggang epsilon n. Pero yung epsilon neighborhood, yung epsilon sub I neighborhood around X ay nasa loob ni O sub I. Pero gusto ko maging nasa loob siya ng lahat ng O sub I's. So any suggestion for the choice of epsilon? Okay, it's fine kung hindi nyo maisip right now. Pero I hope you will agree na pwede kong i-take si epsilon to be the minimum ng epsilon 1, epsilon 2, hanggang epsilon n. Piliin ko yung pinakamaliit sa kanila. Okay? Kasi kung mas maliit yung epsilon, yung radius, ibig sabihin mas maliit yung set. So halimbawa, ito si A. Tapos halimbawa, ito si O1. So meron akong epsilon 1 na nandun siya sa loob. Pero kung meron akong O2, okay, posibleng yung mapili kong epsilon mas malaki. Kasi kung ito yung epsilon na piliin ko, from here until there, that's epsilon 2. That's epsilon 2. Okay. Yung epsilon 2 neighborhood ni A ay nasa loob ni O2. Pero wala sa loob ni O1. So kaya ang pipiliin ko, ang trick ngayong gagawin ko, pipiliin ko yung pinakamaliit dun sa mga epsilons. So if I only have 2 epsilons, ano yung mangyayari pag pinili ko si epsilon sub 1? So pag pinili ko si epsilon sub 1, kasi siya yung mas maliit. Yung neighborhood with radius epsilon sub 1 ay nasa loob ng neighborhood of radius epsilon sub 2. Pero yung epsilon sub 1 nasa loob ni O1. Yung neighborhood with radius epsilon sub 2 ay nasa loob ni O2. Pero pag pinili ko yung mas maliit, you will see that the epsilon 1 neighborhood is inside O1 and the same neighborhood with radius epsilon sub 1 is also inside O2. So pwede ko siyang piliin. And imagine what will happen if you have, say, 100 such epsilon neighborhoods. Piliin mo lang yung pinakamaliit. Ibig sabihin, laging nasa loob siya nung lahat ng mga epsilon neighborhoods. Okay? So I hope that made sense, yung geometric argument. So then I can say here, yung B sub epsilon of x would be a subset of B epsilon sub I of x for all I from 1 to n. Kasi nga, mas maliit yung radius. So nasa loob siya ng mga epsilon neighborhoods na mas malalaki yung radii. Okay? Pero alam natin na ito, bawat isa sa mga neighborhoods na to ay nasa loob ng respective OIs. And this would be true for all I from 1 to n. Ibig sabihin, yung epsilon neighborhood ni x ay nasa loob ng lahat ng OIs. So therefore, dahil nasa loob siya ng lahat ng OIs, ibig sabihin, yung B sub epsilon of x ay nasa loob ng intersection ng lahat ng mga OIs. Nasa loob siya ng bawat isa sa mga OIs. Therefore, nasa loob din siya dun sa intersection ng lahat ng mga OIs. Okay? Which is basically the set O. So we have proven here that there exists an epsilon, namely the minimum between epsilon 1, epsilon 2 until epsilon sub n, such that the epsilon neighborhood is properly contained in the set O. Actually, mali. Hindi siya element, siya ay subset. Okay. So therefore, actually, the intersection, which is the set O, is an open subset of R. Okay? Kapagod, no? mag 1 hour 10 minutes na yata akong nagmo-monologue. So, what do you think? Kaya ba itong gawin pag kayo na lang mag-isa? Pag sa prob set, ganito yung gagawin nyo. So, what do you think? Or medyo nakikiramdam pa kayo? Let me just see, what do I need to discuss more? Okay, questions? Wala talaga, guys. Or nahihiya lang kayong magsabi? Sige, habang I am catching my breath, share naman kayo. Come on, guys. Bawal mahiya. Okay, so maybe I'll stop here. Pagod na ako eh. So that means there's still a chance that homework number 2 will be moved probably to Friday kasi matatapos ko yung coverage niya on on Tuesday. Okay? So wait. Can you let me know kung online pa ako kasi nag-text na yung Globe, nag-expired na raw yung subscription ko to data. Am I still online? Or baka nakipag-usap na lang ako sa laptop?
Yes, sir. Online.
Okay. Wala lang talaga kayong reaction. Okay. So, all right. So, I think we'll stop here. Medyo baka information overload na. So, on Tuesday, we'll talk about limit points. And I guess after limit points, let's see. So we'll have isolated points. I have closed sets, closure, perfect set. So kukunti na. Kaya na natin to on Tuesday. At tama nga ba? Ang first problem set nyo ay pagkatapos ng Unit 1. Let me just double check para ano ko na kayo. Para magka-idea na tayo kung kailan yung problem set number 1. Hanapin ko yung course guide. Saan ko ba siya nilagay? Okay, there you go. I think per our course guide, the first problem set would be on the week of October 4 to 8, and its coverage would be Unit 1. Okay, so medyo matagal pa naman pala. We still have actually 2 more weeks before the first problem set. Okay? So any questions? Or pagod na rin kayo? So if not, let's call it a day at this point. So I hope you enjoy the rest of the night and enjoy your weekend. Weekend na pala, next week na pala tayo magkikita-kita. So thank you for coming today and let's see each other again on Tuesday. Bye everyone.
Thank you
Thank
po,
you.
sir.
Yes, sir.
Salamat po.
Thank you po, sir.
Yeah, you're welcome. I'll